Afternoon, everybody. Good morning, good evening, wherever you are. I'm the head of remote sensing and products. My division is in charge for all preparation work for future missions, as well as the constant evolution, calibration, validation, and data quality of existing missions. And here I'll give you in the next 20 to 25 minutes an overview of what we do, what we've been preparing for, and giving a few examples of certain activities and certain themes that we are pursuing either as direct products or applications. Oh, my slide over, okay. So first, EUMETSAT is currently flying 11 satellites. Those are broken up into two main programs, one being the mandatory programs. This is really our meteorological missions. This is the ones why EUMETSAT exists. It's the support to numerical weather prediction and weather forecasting. And there, this is a combination of two sets of satellite types. One, the upper ones, the geostationary satellites that are located at essentially over Africa at 36,000 meters, taking frequent measurements, frequent images of the disk that includes Africa and Europe. And this is complemented by the polar program, low Earth orbit satellites at about 700 kilometers. We have a fleet of 3 currently in the meteorological programs. This is the METOP series of satellites. Those are platforms that have about a dozen instruments that have a local crossing time of 9:30 in the morning and have global coverage. Complementary to this, we have our optional third-party programs, which includes also the European Commission funded Copernicus Sentinel satellites and also the adjacent satellites. And those have, to a large extent, currently a focus more on marine applications, although there's also some atmospheric products being generated from the Sentinel-3 series. To the right side of the figure, you see essentially what our next generation satellites will be. These are in the geostationary family, the METEOSAT 3rd generation. Those are the two top at the far right. In the polar programs, it's the METOP 2nd generation, the A and B units that will be starting in 2022. And down at the bottom, you have JSON CS, which is also called Sentinel-6, which is a climate continuation topography mission for sea surface height. Now, as part of our mandatory programs on MTG and on METOP 2nd generation, we will also be hosting, in agreement with the European Commission, of course, Sentinel-4 and Sentinel-5. Those are air quality specific missions, and they will be also part of our satellites. So, I mean, really, our core activity is to really member states. And here I have an example of what the METOP series, our low Earth orbit satellite sounders, are providing for NWP. And on the upper two panels are our microwave sensors. On the bottom right, bottom left is our infrared, high resolution infrared sounder YASI. And on the bottom right is our visible near imager, optical imager called AVHR from the long series, in the family of the long series AVHR. This is an instrument that has been hosted, that is hosted from NOAA on our platforms. And those data, and here what you see is animation of the different channels and the radiances over the continental United States at the time where there was a hurricane off Florida, Hurricane Dorian to be more specific. And it just gives you an idea that from the slew of instruments on our METOP series, that all of this information is provided to modeling and forecasting centers such as the UK Met Office or at ECMWF, as well as shared with our colleagues at NOAA for their GFS system. Of course, All of those measurements have different properties. Some are profilers, others are imagers. And as you can see here in the case of a zoom in of the YASI image, which is the bottom left, you can see that the resolution, of course, is rather coarse. However, the information content is great. And there, as you can see the outflows of the hurricane as well as the hurricane itself over Florida. Now, the thing is, we've become so accustomed to good weather forecasting. One of the big questions is, of course, with all of these measurements that are done from low Earth orbit satellites, what is their impact on actually forecasting of a hurricane? And here's an example of the forecasting of Irma. This is a hurricane that crossed the Atlantic in August 2017. And it is actually an exercise that has been done by ECMWF by withholding the NOAA and EUMETSAT measurements from the forecasting system. So at the top, what you see, the upper two panels are the forecast with the satellite information, where you see the buildup of the hurricane and the wind speed very clearly as it approaches the outer Antilles. And at the bottom, what you will notice is that essentially not much happens. This is just another demonstration of the importance of this data and their impact on numerical weather prediction. Now, of course, our mandate is clearly providing this information for the purpose of meteorology, but many of these instruments have capabilities that can also be exploited for other application, other purposes. And I'll start showing you some examples. The second set of satellites that I was mentioning are geostationary. And here, this is an image of a thunderstorm formation close to the Pyrenees in northern Spain. And it is just showing you the combination of the two meteosat satellites that are operating in parallel. On the left-hand side is the nominal 15-minute scan. This is a measurement mode that covers the whole disk of geostationary measurement. That means Africa and Europe every 15 minutes. And the 5-minute scan, or the rapid scan service, as it is called, is a 5-minute scan that is focused only on the European part of the disk. And what you can see between the two, these are complementary information, is that on one hand, you see a bit like a step function between the images, and you see really this discrete buildup of the storms, while on the right-hand side, you see how the storms actually build up, and you see the flow of the clouds and the structure. And this is really important because as the LEO provides a lot of information for numerical weather prediction, what the geostationary satellites provide is information for short-term forecasting or nowcasting. Here's another example of what you get from geostationary. As you will recall, 10 years ago already, the second eruption of the Eyjafjallajökull Icelandic volcano happened. And on request of our member states and also WMO, EUMETSAT developed monitoring capability that is provided to aviation and the VAX. And here's just an example of how the plume builds up over the days and how this can be followed from the geostationary geostationary platform quite effectively. The other thing you also see, of course, is, which is depicted in brown here, are the buildup on the fronts, the clouds moving across the Mediterranean very clearly. Now, I mentioned earlier complementarity. Many of the instruments we have can do a lot of things. Of course, for us, meteorology is always the most important thing, since it is really our mandate on our day-to-day business. But there's other aspects that have become more and more important for users and for our member states. Among those is, of course, air quality and the quantity of aerosol, the type of aerosol, or actually pollution in general. And here's an example of the Australian fires of last winter. As you recall, this has been a long-going incident over 6-7 weeks with tremendous fires. And here what you see is essentially from our METOP satellite, a combination product that measures both the actual aerosol optical depth, as well as certain features in the aerosol, including coarse particles or smoke. And here what you see is essentially over the course of a few days, how the aerosol carries over from Australia all the way to South America. Of course, since we do not just operate, we also need to develop and constantly improve or address quality issues in our product. We also use here, and this is our second figure that we have here, is data that is using the multi-viewing capability of the Sentinel-3 SLSTR instrument. This is an instrument that measures, has two viewing geometries, one backwards at 55 degrees and one to the sub-satellite point. And there, what we're doing is looking at the same aerosol properties, aerosol optical depth in particular, but trying to understand what we can do to further improve the aerosol measurements. And this is just an example. What you will already see here is an improved resolution as opposed to our nominal PMAP product at the top. But, and you will also see, because of the improved resolution of the sensor, you have less cloud issues. There's still a lot of cloud issues, clearly, but you do have a bit more information. And this is something where we look at. So the lower part is currently an R&D product that we are essentially playing with in preparation of our future missions. On the LEO satellite METOP, one of the instruments is YASI. This is a high resolution infrared sounder. This infrared sounder allows you not just to measure temperature, humidity, ozone, but also other trace gases and constituents, among those volatile organic compounds, but also carbon monoxide, methane. And here, it's just a complementary figure to the previous ones on aerosol, but looking at carbon monoxide as the cloud that is generated over Australia is slowly traveling across the Pacific to South America. This composite figure has been generated at EUMETSAT, and it uses the information from all three of our flying satellites, namely METOP A, B, and C. Another aspect from our low Earth orbit satellite is that instruments that were originally designed, for example, the scatterometer, to give surface winds over oceans, also have measurement capabilities for soil moisture. This is a development that has been done through our satellite application facilities, namely in this case the hydrology SAF that is run by the Italian Air Force in Italy in cooperation with the Technical University of Vienna, and also the CNR IRPI in Italy. And there, this secondary product, soil moisture, also has triggered another application that is very interesting, which is essentially trying to use the information from the scatterometry soil moisture as a natural rain gauge. And essentially, if you look at the complex topography here of Italy, those are real measurements. Those are actually measurements by rain gauges. And you can see how this accumulation and how the topography signature in the north and also across the Apennines are very visible, as well as down in Calabria. And essentially, this was an experiment and an idea by Luca Brocca of CNR to try and apply this and see what would happen. And as part of this application, SM2 rain, as it is called for the ASCAT, has been tested with the 12-kilometer resolution. And this is the result you see on the right-hand side. It is essentially a scatterometer-based, soil moisture-derived, rain gauge product, SM2 rain. And as you can see, the agreement, of course, qualitatively here by comparing the two figures, seems to be in quite good agreement. Again, an example of an application that was not foreseen both as a product in soil moisture nor as a rain gauge in the case of the SM2 rain product in the original definition of the mission. And this is something that is, of course, something that we welcome, and our member states welcome, and we, of course, encourage this kind of research and development and new product developments. Another application here with respect to SM2 rain, which is very important on a hydrological basis, as is the rain gauge itself, is to see how you can accumulate precipitation. And here's an example of another hurricane. This time it's Idai, that was off the coast of Mozambique in March 2019. You can see on the left-hand side the hurricane as seen by AVHRR on the METOP series satellite. In the middle is the microwave-derived precipitation product from the Global Precipitation Measurement. This is a JAXA-NASA mission, and you can see how the rain is over the course of those 10 days fluctuating on the stationary hurricane. On the right, you see the accumulation, the rain gauge, the virtual space-based rain gauge of SM2 rain, and how this is building up, and how the quantities of water have been destructive on the coast of Mozambique. So, looking at the future, we are now developing the third generation meteosat, or MTG, as well as the second generation METOPS, or EPSSG as it is called right now, and just giving you a bit of a European context. The meteosat program, which goes back to 1986, sorry, 1978, wow, I'm terribly sorry, here, is essentially a success story when you see it from a European perspective. We are looking at 40 years of data through 2 generations of systems. We are currently flying the second generation, what I showed you the images earlier, and we're developing the third one. This is now also a major asset and has been adopted, has been included in the EU space strategy in 2016. Now, both programs, and this is a really important point, have been fully funded by the 30 EUMETSAT member states. This is, of course, at an order of about 7 billion euros through the 2040s. So we are looking at a very long perspective of fully funded activities there. ESA itself builds the satellites, have through their own programs also contributed to this. The first satellites, in both cases, MTG and EPSSG, will be launched in around 2021-22 and will be operational already in the frame of the Horizon Europe, the research program by the European Commission. So some of the things we're doing in preparation of the new programs, as I mentioned earlier, the high frequency repeat rate of the geostationary satellites are very useful for short-term forecasting. In the new platform, there will be more instruments. These will not just be the imagers, where I showed you both the animation of the storm or also the volcanic ash plume, but there will be also an infrared sounder, there will be a lightning imager, and there will be over Europe an air quality monitor. Those have very high temporal repeat rates, meaning that they will be measuring the full disk every 10 minutes with the imaging, the lightning as lightning happens, the air quality from the Sentinel-4 platform on an hourly basis, and every 4 hours the complete disk will be measured with the infrared sounding, but Europe will be measured every half hour with infrared sounding. So as part of the preparation here, we've been looking at specific examples and test cases to see if, for example, the profiles that we derive from hyperspectral infrared sounding, YASI on the low Earth orbit, and IRS, the infrared sounder on MTG, how good can they be, and how useful are they for nowcasting and for short-term forecasting. And this is an example here of a thunderstorm that built up in Bordeaux a couple of years ago. And this is a thunderstorm that was very interesting, not just because it caused dramatic pictures, as you can see at the bottom. It had an economic impact. It was rather destructive on the wine industry at the time. But what was very interesting in this case, it was not forecast as a significant storm before it happened. And as we started investigating our measurements, and we started looking at the instability factor, what we saw in this case is that the measurements by YASI, which only happened at 9 o'clock in the morning or 9:30 in the morning, actually already detected some atmospheric instability, which would have been an indication for the forecasters of Météo France to most probably follow this storm a bit closer and see into what it would build up to. Now, keep in mind that on the 3rd generation METEOSAT, the measurement of that area will not be twice a day, as it is right now with the low Earth orbit satellite, but it will be every half hour. So for short-term forecasting, if you start seeing instabilities, you could monitor and see, is this instability getting stronger, or was it a false alert or something like that? And this is the type of research we are encouraging right now across our member states, and also with researchers both in Europe and in North America, to investigate specific cases more and to try and better quantify the performance of hyperspectral infrared sounding products for nowcasting and specifically for instability and storm forecasting. Another product that is very important in numerical weather prediction is wind. And wind, as you can imagine, is measured by the ESA mission with very good results.
Boyan, sorry
also,
to
here have a capacity, yes?
Sorry to interrupt. We just lost you for about a few seconds. Can you start again with this slide?
Okay. Okay. Thanks, Stefan. Wind is a critical parameter for numeric prediction. It is something that is sparsely measured conventionally. There's some surface instrumentation, mostly ballooning, 3,000 a day approximately on average globally, but they are sparse in time both and in location. And there is currently an experimental mission by ESA called EOLUS that allows you to get through LiDAR Doppler wind curtain. Now, what we've been looking, because of the repeat rate of the on MTG, the potential to see if we would be able to derive wind profiles based on the change of water vapor, ozone, and temperature fields as measurements are taken. So looking at every half hour and looking at the change within that half hour of the fields. What you essentially see here is a demonstration that is done with our YASI instrument that is flying on METOP. And there, of course, it's a bit more challenging because you need to look at this between orbits. And this is what you see essentially happening in the animation to the right. But the basic idea is to stack the information of water vapor, ozone, and temperature, and to look at the changes in there. And this is very interesting because this measurements themselves and this derivation is independent of any modeling. It is done purely by looking at the profiles of the different constituents and their rate of change between measurements. Again, a field rather interesting numerically, and also looking at the challenges of validation, things like that. Another very good example, this is a piece of work that was done by Martin van Dam and Lieven Clarice from the Free University of Brussels. This is an accumulation of 10 years of ammonia measurements from YASI to get the emissions. This is a paper that appeared in Nature in 2018, and a very nice piece of work. But one of the big challenges, of course, is with a low Earth orbit satellite, as you only pass twice a day over a given site. Your measurements are impeded by clouds, by signal to noise, and you need to accumulate a lot of information. What is going to be very, very interesting when we have a geostationary hyperspectral sounder is that you will still have challenges of clouds and of measurements. However, your accumulation rate and your diurnal variation might be faster resolved. Keep in mind that the measurements will be limited, of course, on a half-hour basis to Europe and over a 4-hour basis over the rest of the disk. But still, this should accelerate the emission inventory capabilities. This also means, because the spectra have so much information, you might be also able to start looking at other trace gases or even looking at emissions of volatile organic compounds at a much higher frequency. Very interesting area, and definitely something that will have a big benefit to both modelers as well as in research and development aspects, just going through the tons of data that will be available. Another example is here. I mean, looking at something that has not been foreseen is looking at snow extent. You would think, yeah, of course, snow is a meteorological parameter. Well, yes and no, not always. It is also challenging to be used in modeling and things like that, but it is very important, and very important for hydrology and water column information. And here, what we're doing in anticipation of our second generation METIMAGE instrument, we have been looking at using Sentinel-3 data from Copernicus and to actually demonstrate the capabilities. Sentinel-3 is a great instrument to use in a lot of the preparation for EPSSG METIMAGE and also for FCI for that matter. And this is a really nice source of data where we are very keen on looking and understanding how the performance of algorithms and the demonstration of the algorithms prior to launch of our next generation satellites. Moving to a bit more, some details on our geostationary satellites, MTG. This is an example of what is really going to change. Essentially, in the past, the frequency of measurements has been rather high, every 15 minutes, but the sub-satellite resolution has not been optimal. It's been on the order of 4 kilometers. Today, with the additional channels that MTG will have in its imager, you will have something that is much closer to the performance of MODIS and VIIRS, or in some cases also of looking at Sentinel-3. And here, this is essentially an RGB from MODIS from 2006, and just showing you what we will be seeing from the imagers, which will be also very interesting for non-meteorological applications. So there will be detection of vegetation and vegetation signs, so essentially surfaces, what is happening on the surface. There will be surface features, looking at certain aspects of this and be able to see them more clearly. Looking at haze, looking at dust, aerosol. Here in this case, we see the plume of Mount Etna volcano quite nicely. And also the repeat cycle will be increased. The complete disk of Africa, and that includes Africa and Europe, will be done every 10 minutes with a resolution of about 1 kilometer at the sub-satellite point. And on the rapid cycle, it will be a much faster 2.5 minutes. So what are the kind of things we're already looking at, and we know that the research community is very interested in, is looking at the daily course and also the better characterization of the certain surface properties. Here, in this case, it's an example of the turbidity. And this is done with Severi. However, this is really in planning of MTG, which will really be able to address that. You will have multiple advantages just because of the high repeat rate. You will have chances to see cloud-free scenes more readily over the course of a day. You will have the higher resolution. Now, all of those activities that we do at EUMETSAT, of course, we always try to tie in back to very clear user requirements, not just for our meteorological product, but also for those where we look at new applications or developments. In this case, this is at a request of CMEMS, or the Copernicus Marine Environment. This is very interesting because you can see some very nice features. And the example here also in the bottom right is of the water turbidity for Lake Victoria. You can see how the fine granularity is there. It's going to be very interesting. And also we go see nice changes over the course of time, over the course of the day. Another example here, and there again, Africa is chosen on purpose because it has very varied aerosol regimes, both driven by biomass burning or by dust flows. And here's a comparison of work we started doing again with Sentinel-3 because of the channel selection, and looking at using the simultaneous surface property and atmosphere retrieval graphs that was developed by Dubovic et al. From the University of Lille in France. And here the comparison is the monthly average for July 2018 between what we are planning, hopefully to implement soon for FCI, but a lot of work is still done on the left using Sentinel-3, and then the latest MODIS collection 6 using Terra, which is time coincident to Olchi on there. And you can see some differences, particularly the transitions between land and water, where the simultaneous retrievals of Dubovik are definitely more promising than the rather abrupt gradients that you see on the MODIS product. Another thing that is rather exciting, and here I am going to be borrowing an image generated by NOAA from their Lightning Imager. They are flying a Lightning Imager since about 2016. This is something that we will be also having on our platform, MTG. This is going to be very interesting for all kinds of aspects. One, of course, is the leading edge of storms and the intensity of storms, but also it will help in quantifying natural NOx, nitrogen oxide budgets based on lightning and things like that. And this animation, you'll just see the kind of thing that we might be expecting. Of course, in the continental US, they have a very strong fronts in Tornado Alley, which you see here with very strong multi-day storm fronts crossing through. We don't always have those in Europe, thank goodness. But what we will be seeing is the buildup of storms as well as their intensities in a similar fashion. It's a very interesting animation, and I encourage you that the presentation will be available to you afterwards to look at this in more detail, because you do see, for example, of Louisiana, how a storm starts building. First you see the clouds, and then you start seeing the lightning, and as it goes up through Alabama, Georgia, up to the middle part of the eastern seaboard. Very interesting. What this brings is that we are finally coming to a point where from space, with the new series of satellites, we will be able to look at the four-dimensional weather cube. Everything from the surface with the atmospheric composition elements, the winds, the convection buildup, and then the lightning. This is a really interesting and exciting time. There's a lot of things in this area that still needs to be investigated, quantified, dated. And there's tremendous opportunities in R&D here to work at this. But it brings to one thing that is really key to in large part to the success of what EUMETSAT has been doing over the last 3 decades, and is really strong today, is that you have this continuous cycle where research to operation and operations leads to research. And this cycle of continuous evolution and implementation and improvement is something that we don't just live, but we encourage, and we encourage especially dealing with the R&D the communities to improve and find new application, new possibilities. Another example here is on our second generation METOP, is looking at the SGA platform. This is the imaging platform, essentially. If you look at 4 of the instruments that are on there, the 3MI, the multi-view, multi-channel, multi-polarizing imager, Sentinel-5, which is the air quality sensor, METIMAGE, which is the imager, follow-on to AVHR with more channels, more resolution, as well as the next generation YASI, which will be even better and more sensitive. What you can do here is to start looking at complementarity of measurements. And here's just one example that has been prepared by Thierry Marbach from EUMETSAT, looking at how those 4 instruments can interact together and how they could actually be really complementary in improving, for example, aerosol parameters from the imagers by being able to better filter and identify cirrus clouds, this being applicable for YASI and Sentinel-5, just by having this. So what we are looking at, and more, and what we're also encouraging, is to start investigating platform synergistic products, where one instrument's capabilities can be complementary to the quality or even to the product generation of another. Another topic that I would like to bring up just briefly is that as part of all of those activities, of course, CalVal is key. Calibration. Without good calibration, you don't have good measurements and don't have good products. Validation is an ongoing process throughout the lifetime of a mission, and even in the post-mortem or in the reprocessing part. Reprocessing itself is critical as new products, new developments, improvements in algorithms come up. Time series ought to be reprocessed, and we do this, as well as the generation of climate records, very specifically targeted climate records, not just instrument records, but climate records. And here, just giving some examples. As part of our scatterometer calibration process, we have ground-based transponders that contribute to this calibration. This reduces the uncertainty in the transponder measurements from about a 5% measurement to a better than 2% measurement. And even some people came better than 1%. What does that do? It allows you to actually generate other products. As I said, the scatterometer was originally designed to do wind over oceans, over water bodies. Now we can do soil moisture and rain gauges. In large part, this is possible because of the good calibration. Here's the example of an example of a 10-year soil moisture record that was generated by the hydrology staff. And what is interesting is if you look at this interim climate data record, if you look at it in a regional case, and this would have been over the Cape Town area of South Africa, this is looking at those 10 years of data, and you can see the times when it is wetter and when it is drier. And what is very clear, you see in the signal, and you can go there into climate monitoring, the higher deviations of the droughts that they had a couple of years ago, where water was rationed to under 4 liters per person per day. Similarly, part of the work with respect to reprocessing is looking at interoperability between sensors. This is an example here from Sentinel-3, where our algorithms and our quality assurance and validation tools have then also been applied to 7 other altimetry missions, including JASON-2, JASON-3, the CNES Indian Saral Altica instrument, and of course Sentinel-3. And this is superimposed over a model of the topographic variations of the northwestern Atlantic. And this is a very interesting example of how this can then contribute to better estimations of climate records and the overall change of the trends in the sea surface height. So MTG and EPSSG with respect to research and development. Well, as I mentioned earlier, MTG and EPSSG are operational programs with clearly a meteorological objective, but multi-purpose. But what is very important, they will be there for 20 years guaranteed. And this is something that is a great asset, because as you develop things and you start building up your understanding of a mission, this mission is going to be around for a very long time. This is a real benefit, both on the science and on the climate research aspect. Both systems, and I just gave you a brief overview, but there's more information in the backup of the slides that will be accessible to you. There's very many new instruments, things that haven't been flown, but there's also significant improvements in existing measurement capabilities, both in the microwave sounding or in the hyperspectral infrared, as well as is it in the imagers, or looking at the new instruments like the lightning imager or things like that. So really, the opportunities for R&D are great, and these new data are a real goldmine for further applications and also improvements of existing application. Complementary to the meteorological sensors that we have on MTG and EPSSG are, of course, the 2 air quality missions that are from Copernicus, Sentinel-4 on MTG and Sentinel-5 on EPSSG. And those, of course, in use of synergy and looking at the complementarity on air quality, for example, I showed you the example of the Yazi ammonia. Of course, this would also help in the whole modeling aspects of air quality or an understanding of physical processes. And this is a very interesting time. The other thing is those data, are we talking about EPSSG and MTG, as well as for Sentinel-4 and 3, are free of charge. They are fully accessible to you. And of course, there's a very basic data policy, but this is there. You are taxpayers. You've contributed to this. You're entitled to using those and developing those and new products from those. What has also been demonstrated already just with the current baseline for MTG and EPSSG, both of those are anchored in solid science as well as very clear end user requirements, have a huge societal and economic impact. Of course, I mean, this is quite obvious when you think weather. Weather is a key element in so many aspects of our daily life. This is an obvious element, but there's also other applications and other things where this can be done. I mean, they can be in the support of transportation, looking at health impact through pollution, looking at greenhouse gas and all the other aspects of climate monitoring and things like that. The other thing is, when you look at all of those things, especially for the future missions, you shouldn't forget that there's some very good existing missions that fly already, where the access is also there. One of them, which I showed earlier, is Sentinel-3. Those can be used in many cases as proxy information to test, validate, verify applications, new algorithms that could be then applied to MTG and EPSSG once they launch. How can we help? Well, one of the main entry points would be through user support at EUMETSAT. There's the help desk. They will guide you to specialists depending on your questions, to experts, or giving you general overviews and information. The easiest way of doing it is through email with ops@eumetsat.in and pose a question. The other thing which I also encourage you is to visit EUMETSAT in web pages. There's descriptions about our future programs. There's a lot of information and brochures available for download, as well as if you go navigating through the science pages, you will find a lot of information on some of our studies, some of our algorithms, and things like that for your information. Also, what is very important, next June, and we're talking June 2021, there will be the MTG and EPSSG user days, and those user days will be very much focused on our core users, meteorology and environment, as well as addressing very specifically research and academia. And we are encouraging you to please follow this and please come and join us in Darmstadt. I would like to thank you for your attention. And here's the last slide, just giving you a bit of a perspective between today, 2020, and 2040 about the fleet of satellites and the launch schedules currently planned, both from our mandatory and our third-party missions. And with this, thank you very much for your attention.